All right, so I'm going to go ahead and get started. I do have quite a bit to cover today. I do like to sort of give decent amount of time to just sort of discussing the exam, just to sort of put things in perspective for you guys. So again, as I tried to mention during the exam, I started to note during the exam that I probably a little bit on the long side, which I think is partly responsible for the lower average of a 43. Generally, my averages are 55 to 60 range, so that was a little bit on the low side, which is hopefully attributed at least partially to the length of the exam. Although I don't want to fully assume that, and I'll discuss it in a moment. So your grades should be on Blackboard, and I always have people ask me, what's my grade correspond to? And I think it's difficult to do because generally what happens is at the end of the semester, I sort of have all the grades in front of me, and I look for, there's lots of things that factor into where I sort of differentiate grades. Like one of the things I'll often do is I'll look through a bunch of the final exams and sort of see how those look in terms of people in different populations and how I think of them just in terms of their knowledge of organic chemistry. So a lot of things like that will factor into my final decision of the grades that are given. And there's other things as well, like oftentimes one of the things that we like to do when we're splitting up grades is look for little gaps in areas so that there's, because inevitably anytime you grade something, right, you're going to have a person get an A or say a person get a B who's actually closer to a B plus than, say, for example, the person, if they're closer to the person with a B plus than they are to other people with B's, right? So, it's sort of what we have. If there was a numerical grading system, it would be a little bit more, I think, easy to sort of separate them. But one of the things we do like to do is look for like gaps so that we can at least limit those differences as much as we can. So asking whether you have an A or an F and then trying to subsequently calculate what your grade is going to be may set you up for disappointment. But at the very least, or maybe not, I don't know. But at the very least, you can sort of get a gauge for how you're doing. So instead of sort of saying A, B, C, D, I tried to put it on somewhat of a color scale. I'm hopeful that, while the average on this one was a 43, I'm kind of hoping that the next exam will be higher. So that's why I've really only put like 80 to 100 as the A's, because I assume that a lot of other people will be pushing up into that region next exam. So just a few things. The one thing that I did notice when I was looking through the exams is there seems to be a big discrepancy. When I ask mechanism questions, and especially there's mechanism questions, in this course, I sort of expect that you guys can all push standard errors. And so I don't want to give a mechanism question where I ask you to show me the mechanism of brominating an alkene, right? Because those types of mechanisms that you can memorize and just sort of see what was in the book, you can probably just memorize it and redraw it. And I think the issue with that is that it doesn't really take an understanding of what the arrows mean. And one of the things that I noticed is that a lot of you guys seem to have a fantastic grip on mechanisms, and then others of you seem to make a lot of mistakes that are hopefully going to get corrected in Organic 1, but can obviously slip through. And those are things like, having an arrow and then having the product that arrow is drawn not represent what the arrow actually means. So doing things like just adding a random carbon to the compound, or having electrons move away from a carbon and then suddenly have that carbon, instead of going to a positive charge, going to a negative charge. So the sort of basics of general chemistry, things like conservation of charge, conservation of matter, tend to fall apart, and the hope is that those things are sort of solved after Organic 1, but I did notice quite a few of you guys sort of struggled on that. So if you struggled on this exam and you think that a large part of it is because of the fact that you really, truly just don't understand mechanisms that much, I would really urge you guys to make that a priority, because I think without a foundation of mechanisms, it's not evident from my exam, it's not going to be a fun next few months, because I view mechanisms as the heart of all organic chemistry, and I don't think that you know organic chemistry and deserve to pass organic chemistry course unless you can push arrows without making major mistakes. Whether or not you get the product or not, I don't really care that much about, but certainly those issues that I just brought up earlier, not understanding that language is, I think, important for organic chemistry, because everything else that you may learn going forward with reactivity, whether it's biochem, when you're learning mechanisms of enzymatic functions and so forth, it's going to require your ability to understand how A goes to B and see how that may happen. So that's my that's what I would suggest to you. If you have any concerns, you feel completely lost, feel free to either come to my office hours or shoot me an email, or you need to, again, there's a learning center, but I would make knowing mechanisms a priority if you think that you might fall into that group, because again, it is perhaps my biggest emphasis, and I just hopefully illustrated the reasons why. But again, my sort of the breakdown, how it sort of gradually gets down from 62 down to 20, I think at least it sort of illustrates that perhaps length of the exam might have been an issue. Maybe synthesis is harder, but some of the mechanisms are a problem. I think question 3 could have been argued to be equal difficulty to question 5, and so hopefully maybe that's an illustration that it was just a little bit on the long side, and that had to do with the lower grades. I was a little bit disappointed with the Strecker. 43, not 43% of people got it right, but that was just the sort of average on that question. A lot more people got it completely wrong and got 0 or 1 than people that got 7 and 10. So, I heard rumblings that people didn't even notice that I had it on there. No, I think will oftentimes come to memorizing. I think that when you guys memorize things, and that's why I try to tell you guys not to memorize things, you can often very easily miss the sort of forest for the trees, right? Is that what I'm saying? Maybe I reverse that. But you'll look at something and you'll miss the big picture. So yes, I might have put R instead of a phenyl group, right? R is a phenyl group. It's a functional group that's changing. I might have shown ammonia and HCN, but ammonium cyanide is the same thing. So it's just little things like that I don't know. I just thought I'd bring it up. All right, so regrade policy. So I sort of separate this into 2 groups. First, there's bound to be some mistake on some of your guys that's some blatant mistake, whether it's an adding mistake or maybe a question was accidentally marked wrong, it was right, or a 0 was accidentally written instead of 10. So just look through. I would urge you guys when you get back to your exams, which you should get back, probably not a recitation today, but because they're getting photocopied today, but probably starting tomorrow, you can start getting them back from your recitation instructor. I would urge you guys to just look through that and just double check to make sure there's not anything like an adding mistake, or I'll post the answer key online, hopefully today or tomorrow. And sort of just go through and compare your answers, and if there's a question that's like right, and it's just marked wrong, and you're like, what's going on? What I would say in those instances is just sort of bring it to your recitation instructor, because sometimes you guys might just not understand why it's wrong, so they can hopefully explain it to you. Or if it's a case that it actually is marked wrong and it's right, then that's an easy fix, right? We don't really, so you can just give it to your recitation instructor, they can bring it to me, and I'll make the change. Things that are more like, a friend got 7 on this, and I got 6. Again, if I get it, but the thing is that from my side of things, I know that there's people that don't go out of their way to try to get an extra point or 2. And so people that are trying to get a point or 2, I think that unfairly gives an advantage over the people that might just accept their grade and move on. So please don't do that. If it's legitimate, if you look through and there's a significant amount of points that you think that you deserve, certainly you're right to request them. What I would say is, what I'm going to do for my first time ever is I'm actually going to set a deadline, and what I'm going to do is, if you guys do have those, I'm not trying to, if you really have a legitimate gripe, I'm not trying to dissuade you, I'm just saying, all the grades come around, and I will regrade the entire exam. That's one of the policies. So just keep that in mind. So you must be really confident that you deserve X more points than you have, because it does happen occasionally that people do get lower overall grades. And what I'll do is I'll just hold on to them all until the 23rd, and then it'll just be easy. I'll just grade them all at the same time. So try to get them. If you have a regrade request, the deadline will effectively be the 23rd. And then around that day, I'll just take a look through all of them, update the grades accordingly, and that'll just make my life easier, and so I don't want to be coming down to the final exam and having you guys start bringing questions about this again. Okay, and then lastly, I don't really think I'm that funny, but I do like that football season allows me a chance to make football references. And I did think when I had a couple students come by, it just sort of, because anytime I have students come by after an exam, I just immediately assume that it's like they're devastated, they need to talk and stuff. And so I'm always like in you know, turn that frown upside down mode. And I think if any of you guys, well, you guys are probably studying for the exam, so you're paying attention, but the Patriots last week got annihilated by the Kansas City Chiefs. And everybody was saying the era of Belichick and Brady is over. And there was a press conference afterwards, and if anybody knows anything about football, or Bill Belichick in particular, he doesn't say that much, and he gets very angry about things. And so he was obviously pissed off about the game, and they were asking questions, and he's like, about the game, and he's like, we moved on to Cincinnati. And they kept asking that, and he's like, we moved on to Cincinnati. We moved on. So his point was, you know, he's not gonna stress out about what just happened. He's gonna focus on what he can do, and what he can do was the next game. And Belichick and I think the Patriots, this isn't just a fan of theirs, but you know, I think they represent real winners, and that focus, except when they play the Giants in the Super Bowl, but that focus of sort of, I'm moving on, you know, this happened, I can only control what I can control, and that's the future, and that's sort of moving on, and that's what happened. The Cincinnati Bengals team, who was undefeated, and everybody was saying was the top of the town and the best football team, the Patriots just went out and killed them, and just annihilated them, and everybody sort of said, all right. And I think part of that is at least representative of this sort of moving on. So with that, I would say, you know, if you fell into that lower cluster, you really feel decimated at this point, and your spirits are really down, you know, I don't mean to completely ignore the exam. You know, learn from the exam, learn from what you did wrong, and try to improve, but really focus on what you can focus on, which is that next exam, and really sort of, you know, moving on to Cincinnati. So we're okay. So with that, again, all your exams should be available on Blackboard, and your recitation instructor should have them. And I apologize for the quizzes. I thought that you guys had quizzes back already. I didn't realize that. But those, I saw Danielle putting them available. They should be available. The grades will be available on Blackboard, and she made the photocopies yesterday, so those should also be available. I think it was like only her section got them back or something. So the rest of you guys should be getting those back also at your next recitation. So yeah, Felix. Was that? I'll post this on my, like, what were you saying?
Yes, you said blue. F, so what's the other?
So I just made so that's why I wasn't going to say this is an A, this is a B, this is a C. It's an array, right? So it's a spectra. Exactly. So I use the color spectra to say, you know, is this an A? I don't know. It's light green. Probably an A. But, like, you know, it's going to depend upon what you do next, right? So, like, you know, I just, you know, yellow is somewhere in between orange and green, right? So it's just the... What's that? Don't worry about the grade. Worry about doing as well as you can on the next exam, and the rest will take care of itself. Yeah? Yes?
So there was an issue the day before the exam.
Huh?
Where it didn't actually got to the
Yeah, I know. It's I don't know why that happened. I don't know how that happened. It was like the day before, right? Yeah.
I know people
Yeah. I mean, no, I remember back when I was studying for a big exam when I was in college, and she was an inorganic professor, Karen Brewer was her name. She's like the nicest woman in the world, and we were all slamming our heads up against the wall in this room, and she walks by and she said that same thing, like, go to sleep, go get some sleep because it's important to be sharp. But no, yeah, that was odd. I'd never had that happen before. And I was like, honestly, I was nervous I was going to walk in and my computer was just going to be like ripped out of the wall and walk into my office because I'd never had that happen before. But, it's CUNY. This stuff, what can I say? When things bad can happen, they will happen. Yeah?
Is it possible to put that stuff on Blackboard as well? Blackboard was down,
I don't know, man. I've never had this problem happen before. What I would say is get the material. Don't wait till the night before, because if you're trying to get all the material the night before and cram the night before, I know you did okay, but you could have, yeah. So life lesson, I guess. But again, on the fortunate side, like I've told people, the average was low, which can be a good thing or a bad thing, right? On the bad thing, it's like, I personally wish the average was higher. But by the same extent, from your standpoint, whatever grade you got, you can make up a lot of ground. So, all right, let's on to Cincinnati, right? Okay. All right, so today we're going to focus on. So today we're going to sort of refresh on a few things with Diels-Alder. I'm going to do another attempt to explain endo rule a little bit better. I did notice that in the book, I think it doesn't really discuss the orbital overlap, but I'll try to show you guys that. Again, I'm not necessarily going to ask you to show molecular orbital overlap, but I think that to understand the kinetics and the kinetic product being the formation of the endo product, I think it's worth it to just recognize that it's generally orbital overlap, because at least that way it makes sense. And then I'll discuss some of the things electronics, a little bit about stereochemistry within Diels-Alder, and then we'll move on to sort of 3,3 sigmatropic rearrangements. So just a reminder, the Diels-Alder reaction is in essence a reaction between a double bond and a diene, and an alkene to generate this product here. Again, formally what it involves, if you go back and you look at the sort of molecular orbitals, remember when we add these up, you have effectively 4 nodes total, but there's none in the first, so you've got full, and then effectively what happens is each time it sort of skips. When there's 1 node, then it'll sort of revert, then on the other one it'll be on the same side. Again, you can go through this or look back at my notebooks, but this is sort of the general idea, is that as you sort of move up, the sort of nodes and which side the external nodes are that are binding are going to go up. So in a situation like this, we're going to have the HOMO on this side of the diene, where we effectively have 1 node through the middle is going to be this diene. And on the other side, we're going to have the LUMO, It's going to be this side. And again, you sort of match up the matched bonds there, and that's going to end up leading to, again, the sort of the product that you get. In this sort of HOMO-LUMO theory, which you can go back and look at my video, or you can read up a little bit in the book. An important point about this sort of HOMO-LUMO isn't necessarily that you guys have a great verse of frontier molecular orbital theory. What I just want you guys to sort of understand is that there is this sort of theory, and there is this sort of orbital alignment, if you will, that takes place at the HOMO and LUMO, which allows for this reaction to take place. And then if you take that similar type of thought process and you translate it to a 2 plus 2 or a 4 plus 4, it should sort of make sense why that wouldn't work. So this is general Diels-Alder reaction. Now, within Diels-Alder, again, the important point is it's the reaction between pi bonds, right? And so I've had people ask other questions about other versions of Diels-Alders, and if you think about it as just being a double bond, or sorry, 2 pi bonds in conjugation reacting with 1 pi bond, this can sort of translate to other types of reactions as well, right? So you might imagine that if you were to have, say, for example, an alkene with, say, for example, an alkyne, right? That's also a Diels-Alder reaction, right? That's going to lead to a product. But if you look at the arrows, you just have to sort of pay attention to what's left over, and in that case, you're going to have 2 alkenes in there, right? So where the triple bond is, you've just lost one of those pi bonds, right? And so what you're left with at the end is still a double bond there. In fact, if you want to get creative, I remember Margot was asking me questions about other types of systems, like could you have, say, for example, an acrylate, and could you have, this is an acrylate, right? So it's a carbonyl. Could that react? And I've actually never seen this one done, so I don't know, but I think it's legitimate. What I have seen done is chemistry with where you do the reaction with like where the carbonyl is the sort of like the equivalent of the alkene, and so you can get to chemistry where you have systems like this. So again, at its core, I think it's just worth it to sort of recognize that this is chemistry between a conjugated diene system and another pi system, right? And so translating this to something like this, or perhaps something like these other things, even though, again, I don't think I've ever seen a Diels-Alder like this, but I think for your guys' standpoint, it kind of makes sense, right? That why not? There might be some factors, though, and there may be a reason why I've never seen those. Yeah?
So when you have, for example, an alkyne,
right.
you have this O with that
an O where?
that which is really high as you have the top structure. So, yeah, that structure. The oxygen bonds to that hydrogen are usually also
See, yeah, that's probably right. So that would be the issue. So the point that's being brought up here is that, and which I'll get into in a second, right? It's the sort of recognition that this is very electronically poor, which may have to do with one of the reasons why this might not behave in Diels-Alder chemistry, because, again, Diels-Alder chemistry is historically classified as, and I'll get into this in a second, but generally when we think of Diels-Alder chemistry, we think of electronically rich dienes with electronically poor alkenes. You can do the opposite. So you could have an electronically rich alkene react with an electronically poor diene. It's just something that they call an inverse electron demand Diels-Alder. So the book really doesn't discuss that, but so you can do one or the other. It's more just about the sort of match, but there may be something more going on that I don't totally understand, which may be why this might not behave, but it could be like what you're saying. Or it might exist. I might just never have seen it. But at least rationally, it should make sense, right? That it's a conjugated 2 pi bonds reacting with 1 pi bond at its core, right? All right, so that's the sort of basics behind the Diels-Alder reaction. So again, go back and refresh on MO theory. But again, I think it's just more important that you sort of recognize that 4 plus 2s can happen, right? And 2 plus 2s can't, and 4 plus 4s can't. Yes? Yes. So yeah, so I'm going to get into that in a second. So the question that Felix was asking is Diels-Alder chemistry going to be spontaneous, right? So we've actually got two questions that I'll answer at the same time, right? So Diels-Alder, like how well a Diels-Alder reaction is going to work, how spontaneous a Diels-Alder reaction is going to work, is often going to be dependent upon how electronically rich, if we figured that what we just said, right? Electronically, because normal, we'll just say normal, what we're generally talking about is electronically rich. And what I mean by that is that could be a system that has donation to it, where you could like sort of stabilize build of a cation character in there through the resonance stabilization through alkyl groups, and I'll give some examples of it in a second. So with electronically poor, and again, this would be the opposite. You'd have groups on there that would withdraw electrons from it. So a reaction, a standard reaction, like the book has a few in actual temperatures that a couple different things will go at. So the book, you know, so in general, the temperature that at least the book gives basically says that if you in the gas phase just take your standard diene and your standard alkene, so just butadiene and acetylene, right? And you effectively mix those together, you can get the Diels-Alder to take place, but you need 200 degrees Celsius as well as a highly pressurized system. So it's a lot has to go in to getting a reaction like this to go, right? The moment that you begin to attenuate the electronics in this way, you begin to make the reaction take place at much lower temperatures. So again, I'll just use the example that the book gives, right? If you take just butadiene by itself and you react it with, say, methylvinyl ketone, right? You can come down a little bit, so you don't necessarily need 180 degrees, or sorry, you don't need necessarily 200 degrees. The book actually says 140 degrees. So it's a much lower activation barrier. If then on the reverse side you actually take this and now make this electronically rich, right? And again, the example that the book gives is that if you take and put methyl groups there. Now, here's the question. Why do those methyl groups suddenly make these more electronically rich? Yeah, I mean, you can think about it, right? Because if this is going to sort of act as, if the alkene is going to act as a nucleophile, right? What's one of the big differences between this acting as a nucleophile and this acting as a nucleophile? It's more substitute, which means the cation is now tertiary, right? So that's the sort of thing that makes that now alkene more nucleophilic, right? So the more substitution on this alkene is now going to help it make it more electronically rich. At least we think about it that way. It makes it a better nucleophile. And so when we substitute in this, again, what happens is now you're basically, for all intents and purposes, at room temperature, and you're getting a product, right? And it goes on from there. I'll actually give you an example where Diels-Alder chemistry took place in my own studies when I was a graduate student. So when I was a graduate student, one of the reactions that I was developing, and we'll learn about one of these steps. Well, we'll learn about one of these reactions later on. So the point of this, I won't go through the mechanisms of the stuff that's not really important. But when I was in graduate school, one of the things that we were working on was this process where we would take a two-step process. So we would take alkenes and alkynes, we'd mix them together under ethylene. We'll talk about this reaction later on in the semester, but I'll just tell you what the product is. It's this diene, right? And then what I was doing was, this was a part of our group where we were trying to take this catalyst, this is just a simplified version of it, these catalysts that we were working on, we were trying to get them to do this, then we were trying to get them to do something completely different. So what I would do is I would take this and I would add a diazo compound to it. So this is a molecule called ethyl diazoacetate. And effectively what happened here in this reaction, again, this isn't really important for you guys to know, but I'll tell you so you know, this ends up doing what's known as a cyclopropanation reaction. It's selective at that position. Again, this isn't, you're not responsible for this. But the product was these molecules like this here. Now, the thing was, is that as I was running these reactions, I kept getting this, you know, and you're trying to develop reactions, you're always up against this sort of barrier that are side products that can be happening. And the side product that we were dealing with the side product that we were up against was this compound that I'm showing you right here, okay? If you sort of work backwards, right, and do a retro Diels-Alder, right, so if you look at this cyclic structure here, and you look at this cyclic structure here, right, you see that cyclohexene in there. One of the things that I may expect you guys to do, say for example, to sort of consider, again, is every reaction is reversible, so just in the same way that aldehydes, you do retro-aldehydes, Diels-Alder, you might be able to do a retro Diels-Alder, right? At least in terms of a retron, and thinking about where this could come from, right? It's effectively that bond. Basically this and this. Now it turns out that this molecule is a product that's taking place because when the metal is doing this, it's also dimerizing this and making this compound here. So this was happening spontaneously. So that just sort of goes to show, in this instance, again, we have a very electronically rich diene, right? We've got that phenyl group at that position. We've got a very electronically poor dienophile. Again, it's got carbonyls at both sides. And so as we were doing this chemistry, we kept getting this side product that sort of resulted from a Diels-Alder. So here's just an example that sort of answers, I think, your question in a way, Felix, which is, do you need to do anything special? And the answer is sometimes, but sometimes it just happens. And this was an example in my own studies where it was pissing me off because I didn't want this. I wanted this, and yet this was being converted to this based upon these side reactions. So that's just an example that shows that they can happen. I think we were elevated temperature a little bit. I think like maybe, no, because we were in DCM, so we were at reflux DCM, which is like 36 degrees. So we weren't even all that hot, and it was still happening. So yeah, but there could be things you can do. The book doesn't really discuss this, but one thing that you might be able to do is, let's say, for example, you've got this reaction here. I'm going to just pose this question to everybody, okay? If you want to make this reaction or even this reaction go faster, what's something you might be able to do? Yeah? How? Is that, no, hold on. Well, so you can modify the compound, right? I mean, one thing that I can do is just add another carbonyl here, but if I want this product, I heard something over here. Yeah. Well, no, we're not going to change the structure. We want this molecule. What additive might we be able to do? Felix, no? Yeah. Effectively, right? Yeah, Lewis acid. So what you could do is, again, you could make this even more electronically poor by adding something in there that might, like say a Lewis acid, that might actually activate that and make it more electronically poor. And so in fact, the book, I'm not going to go into this, but the book discusses Diels-Alder chemistry catalyzed, or sorry, not catalyzed, it discusses like this chiral auxiliary approach. I'm not going to really discuss that. But in fact, you can actually use this type of activation to actually use catalysts that would then install, we talked before about asymmetric catalysis and inducing chirality. Sometimes these catalysts can do that as well, yeah.
So if I want to make something more electronically poor, do I have to add another
Well, that's effectively, yeah. So there's Lewis acid. You can activate, especially if the question is there something there you have to think through the mechanism, right? In this case, if you take a ketone and you treat it with a Lewis acid, right, there's lone pairs here that could coordinate to that Lewis acid. So say, for example, you had triethylborane or something, right? The borane would complex to this oxygen, and that would make the overall system more electronically poor. So you're effectively souping up the electron poor nature of the alkene by having a group here that effectively puts a positive charge here, right? Because now that sort of resonance form becomes even more pronounced, if you can think about it that way. Okay? I don't want to go nuts into sort of catalyzing Diels-Alders, but that's just to sort of explain the point that Thiel's from. So yes, you can. But just think about it mechanistically and think about it as you have an electronically rich this, an electronically poor this. The more electronically poor this is, the better it'll work. The more electronically rich this is, the better it will work. If you can add something that's going to make that be even more electronically poor, or make the other one be even more electronically rich, that can accelerate the process. But whether or not you need to do that, and whether or not that's even going to have an impact, is going to be based upon the reaction. Yeah?
This is like a 1-4 addition, right?
So, okay, yeah.
Is there a way to make it do a 1?
Okay, what time we have? Okay. I was going to look at the time when I got to this part, and I was going to tell you guys another story that depending upon whether I had time, that I think answers your question. And I think it ties in the chemistry that we just learned with, it's a story that you guys, now that you know Diels-Alder chemistry, now that you know enolate chemistry and mycochemistry and everything else, and conjugate additions and so forth, that you guys might be able to appreciate a little bit. So back, again, when I was in grad school, enzymes do lots of things, right? Enzymes will catalyze lots of different processes. And back in about 2000, well, what does this say? 2005, I think? Yeah, you guys even born yet? Does that make me old? God, 2005 makes me old. So there was this reaction that they found that was catalyzed by an enzyme. Okay, and the net product is a Diels-Alder product. I think this is kind of interesting, and it's at least a story that you guys can appreciate a little bit. So basically, there was this molecule here. Under basic conditions, it was sort of existing as this form. It's not really the entire point of it, but it had this sort of form to it. And the product that they were getting out of it, right, is that you have a diene here, right, and you have your alkene over here. So while this might look a little bit more complicated than what we've been drawing, if you just focus in on those functional groups, right, sort of don't worry about the rest of the big picture, focus in on those functional groups and then draw on the rest of the spinach afterwards, right? What they were getting was effectively the product that would result from Diels-Alder chemistry between this and this product here. And so it was being formed okay, and so what this resulted from was, so the purple would be here, right? And the blue guy would be this right there, right? So the bond that we're making, if you guys can sort of see that, right? It was this Diels-Alder. Now again, this is where sometimes drawing molecules and seeing the molecules, that is just a Diels-Alder, right? But then you add everything else and it makes it a little bit difficult to see, and so forth. But this was the Diels-Alder that was taking place, okay? And what happened was, at this point, there became this huge debate because the authors that described this enzyme that carried out this process, nobody had ever known anything about a Diels-Alder ACE before, or a catalyst that would carry out a Diels-Alder reaction. So when I was in grad school, I just remember hearing everybody talk about Diels-Alder ACE this, Diels-Alder ACE that, because it was pretty cool. Diels-Alder
is one of the most powerful synthetic transformations that we have. You know, it makes two carbons at the same time. It can make multiple stereogenic centers at the same time. So it creates all that. You can see it right here, like how you guys said, somebody said, damn, right? The complexity that this is built right here is pretty high, right? These don't look nearly as complex, and then suddenly you do the Diels-Alder. It's like, wow, that's a lot of complexity that's built really quickly. And so there's a lot of excitement of, oh my God, enzymes might actually be able to carry out and facilitate Diels-Alder reactions. But then you had the Debbie Downers who came in and looked at the reaction a little bit, and I think asked exactly what, that was just asked over here, which is, well, is it a Diels-Alder? Or could it be a different mechanism? And the mechanism that's involved, was proposed, actually involved this, okay? So the thought was, well, what if all it is instead, what's that reaction? The Michael addition, okay? So that's the Michael addition. Okay, so I'll try to draw the bond that's being formed here in a second. Okay, so again, that might immediately look a bit more complicated because I'm drawing in 3 dimensions, but the bond that I just made is this one right here. One here. So it's basically the alkene here, right? Looks like right, so it's this guy here. Right, and again, I'll just put the color coordination to see it. And again, you're not going to get this on an exam. I just think this is kind of, maybe on the quiz, yeah. What's that? No. Would you guys want me to tell you this one? No. Good. All right, so then what happens is you're at this compound here, okay? And what this is, again, there's another, drawn this very poorly here. Okay, there's a resonance form, this might get a little bit easier to see, but I can draw a resonance form here. Where? Yeah. Okay, so that's just a resonance form. All I've done is I pushed the electrons from here over to this carbonyl, and then an aldol reaction. So the idea here was that you had some people saying, this is an enzyme that's doing a Diels-Alder reaction, and then you had other people that are saying, well, it looks to me like it's just doing a Michael addition followed by an aldol reaction. And so there are instances where the question of whether it's concerted, right? Concerted meaning at the same time, like a Diels-Alder, 4 plus 2 taking place at the same time. That would be concerted, would be a Diels-Alder. Or is it stepwise? Which could be an example, I think, which is kind of the question that you're asking, is could it be a stepwise process? And the answer is, yeah, I mean, those are 2 possibilities that are going on, and this sort of represents one example where you had some people proposing a Diels-Alder reaction, and you had other people proposing Michael followed by an aldol reaction. Yeah?
I think that if there is like a stepwise mechanism, you should be theoretically able to isolate.
Maybe. Depends upon what the rate limiting step is, right? Can you isolate out this intermediate? Right? So that becomes the question is is a stepwise process. If the second step happens way faster than the first step, then how are you going to figure out those intermediates? Yes, there are ways, and all these papers came out studying it. That wasn't really the, I'm actually not quite sure. I should have probably, I just wrote this down this morning because I was thinking about it, so I didn't get a chance to look in. But what I do know is that recently there was a reaction that was a Diels-Alder that definitively couldn't be anything else. So there are Diels-Alderase enzymes, but again, that was just kind of something interesting that happened. Well, I thought was interesting when I was a graduate student, but it could have just been because everybody was excited about this new class of enzymes. But again, it sort of represents, that's not that long ago, right? And you guys have learned now Diels-Alder, you guys learned Michael-Aldol chemistry, and so you guys can appreciate the sort of debate at a more, not that long, it wasn't that long ago. God, it was almost a decade ago. All right, anyway, yeah.
Is there a reason why you got the 3, or
I may have just omitted something. It's possible that I just typed it. Oh, yeah. Yeah. That's what you're talking about. Yeah.
Could you check for the reactions for different products with the dynamic versus kinetic?
Yeah, I mean, everything gets thrown out the window once you start talking about enzymes because then you have to worry about, it's not like just solution phase chemistry. It's
Would it always be?
well, because the problem is that you have a catalyst, and the catalyst is the enzyme. And what you can think about, if anybody saw the Vern Schramm talk last year, a Friedman lecture, sort of idea was that like an enzyme, I don't want to get suddenly into biochem too fast, but I'll just say this and then I'm going to move on. But enzymes, you can think about enzymes as molecules that bind to the transition state, and that's how they have to kind of catalyze the process. So, in a sense, that would suggest that would a single enzyme do both steps, which might have been one debate. Maybe it could be, certainly it's possible, but they seem to want it to be this single transition state, which may be the Diels-Alder. But the problem with that is then if you start heating it or cooling it or letting it go longer, because it's the enzyme that's actually doing everything, there's likely going to be, you're probably not going to get, you're going to get whatever the enzyme tells you. The enzyme's not suddenly going to give you, you're not going to allow it to go to thermodynamic control necessarily. All right, let's move on. Okay, just a couple more things about Diels-Alder, and then I'll move on to sort of cold chemistry. Okay. All right. So the one other thing that I think you guys should be aware of within Diels-Alder chemistry is, and let me just see, because your book had really good pictures of this. Okay. So your book has good illustrations here on 853. And so I'm just going to sort of talk through a bit of them because I do like how they sort of diagram this a bit. So when you do Diels-Alder chemistry, the sort of stereochemistry of depending upon what the stereochemistry of the alkene is, that's going to dictate the stereochemistry of the product that you're going to get, right? If you think about a standard Diels-Alder reaction with two groups here, you can get two possible products. And those products are going to be dictated by the stereochemistry of the alkene that you have. Okay? So if you think about this group, right, it's got, and we can draw on the protons as well. Right, and the same thing down here, we can draw the protons in to be complete. But you can see that on the cyclohexane ring, and I'll explain this in terms of the concerted nature of the reaction in a moment, but just very quickly, just looking at this, you can see that if the if your alkene is trans, right, the product that you get on the sort of cyclohexane ring is also trans, okay? And if you have a cis alkene, it's also retained. So that stereochemistry on the cyclohexane is also cis. So the trans will effectively lead to them both being on the same face of the molecule in the cyclohexane ring. If they're on the opposite side, trans, if they're opposite, it'll be opposite. If it's opposite of the alkene, it'll be opposite on the cyclohexane. If it's the same side, then that will just translate. And that's due essentially to the fact that this is a concerted process. This is a result of the concerted process. In part because if you sort of think about the general approach, I'll just say R. Right? We have our protons here as well, but I'll leave them out. But as you're forming that bond, right, if it's coming from the top, it doesn't really give the molecule a chance to, say, for example, rotate around the bond or anything like that. So as it's coming in, you're making this bond. If I were to sort of draw this out, right, you can see that the hydrogens are going to be on the same face, right? So as it's sort of reacting, as you sort of bend it out that way following the reaction, what you're going to have is effectively the protons on one side and the esters on the other. Now, it doesn't necessarily mean that you have to draw this transition state to be able to see it. Well, you know, I mean, you guys could probably remember that, right? If it's on the same side, it's a concerted process, so you're not suddenly going to get a rearrangement of where the bonds are. The protons are going to remain on the same side as one another. Anything else, where everything is in relationship on the alkene, if they're on the same face of that alkene, and they're going to be on the same face of the molecule in the cyclohexane. If they're on the opposite, you know, or vice versa, right? Does that make sense? Okay. So moving forward, we can sort of take this to the next level, right? And start to ask ourselves, well, there's the stereochemistry of the alkene, and I think that's kind of easy to see. Where the stereochemistry might become a little bit more difficult is when we start considering the stereochemistry of the diene, okay? So let's sort of discuss the diene a little bit. Now, one of the things to remember, I've sort of done this, right? I've sort of done this on purpose a little bit, right? I've always made the diene exist in this form here, right? This is what we call sort of S-cis conformation, okay? What that means is that the two alkenes are effectively cis to one another. They're together. There's also the S-trans conformation, though. I don't know. What is it? Sigma bond? Yeah, I guess that would make sense. Yeah, so sigma, yeah. You read the book probably. I don't. All right, so anyway, the idea is that this is the sort of nomenclature to them. So it's S-cis and S-trans. I never even really considered what it meant. So usually I do, but I don't know. Anyway, so that's interesting. So around the sigma bond. I like that. All right, so anyway, this is most likely going to be lower in energy, not necessarily in all cases, but you could imagine that the S-trans is probably going to be a lower in energy state, right? But in order to do Diels-Alder chemistry, you're going to need them to get into that conformation. That should make sense, right? It's a concerted process. You're not going to have one alkene react and then suddenly the other one's going to wrap around and react secondly, right? It's all going to happen at the same time. So you need to be in this S-cis conformation, which I've been drawing. But it's important to recognize that occasionally, right, when we start talking about stereochemistry resulting from the diene, it may be important that we sort of recognize and are able to redraw the molecule, right, from the S trans, because we might have a molecule drawn in the S trans that we want to do Diels-Alder chemistry with, but we'll have to be able to redraw it, the S cis, before we can begin to do the chemistry. So that's the first thing to recognize, right? And so let's just do that really quickly as like as a thought exercise, right? Okay, so if both of our alkenes are trans, right, and we rotate around that bond, right, all that we really have to do is make sure that our alkenes here, we're not going to suddenly make this cis, right? We're just rotating around the bond. Okay? So when we rotate around this bond, this is trans, double bond here. This is a trans double bond over here. So it's just important that when you draw into the S-cis conformation, that you just pay attention to the stereochemistry at the alkene. Okay, I'm just going to preempt that being a problem, because I know that sometimes redrawing things, we can have slip-ups. Right? So just pay very close attention, you know, to that diene, right? Now, there's one important thing to note here. If we take this bis-cis compound, or molecules where we have substitution at positions like this, now if we try to redraw it, what do we notice? Collisions, right? So this is something to keep in mind as well with Diels-Alder chemistry. It's the fact that you need to get that S-cis conformation. You have to sort of pay attention to this a little bit, right? Because sometimes you might have a molecule that's not going to be able to exist in the S-cis form. So chances of you being able to get a molecule, again, it's probably going to depend upon the sizes of the R groups. You know, if they're both smaller, maybe if they're both, say, for example, I don't know, fluorine or something like that, or ethers, I don't know, I don't know. But I'm not saying it will never work, but you can have significant issues here because of that steric clash and that. So you probably, you know, this might not work. So just something to sort of keep in mind. All right, moving on to the stereochemistry of the product. So we won't worry about this one at all, right? But we'll worry about this sort of the two other options. The last one being, we won't worry about this one for reasons I just said. But what we will consider as well is this one here, right? Where one is cis and one is trans. So both trans, fine. Both cis, we're not going to worry about that because then it would probably be too much strain. But if one is cis and one is trans, then we'll be okay. Because while the one will bend in, right, the other one will be away from it. And so you can imagine a system where whichever the smaller of the two R's is might be able to sort of fit inside there, right? Okay, so now let's think about the stereochemistry that's going to take place when these happen. Let's just draw a compound like this, okay? Again, it's a concerted process, right? So now that it's drawn in this way, right, we've got our protons here, we've got our protons here, right? When we come in and we react, right, what's going to happen, right? The R groups are going to stay on the outside, the protons are going to stay on the inside. I'll draw it in the endo form, but I'm not really trying to make a point of that right now. Okay, so I'll draw it in the endo form, but again, as this attacks, right, the compound, what we're going to end up with is our R groups, and again, our R groups, when we react, and it comes in and forms it, the protons are now going to be sort of on the same face, and the R groups are going to be on the same face. So what you'll have here is a situation where, and then I'll try and draw this. And I'll use the, okay. Okay, so again, they're sort of on the same, Make sure I can draw this so that you guys can see it. So your book does a really nice job of drawing it. I'm going to try to, so if you look in 853, they might, I'll try to do it here, but if I fail miserably for you, just turn to 853 in your notebook. And they have a kind of a nice drawing for it. So what they sort of show here, and the way that they draw it, is they actually draw it coming in and out of the plane. And sometimes that's a good way to redraw things. Oftentimes when people ask me about chemistry of doing stereochemistry at alkenes, and a lot of times on the alkenes, if you, instead of trying to make the alkene on the plane of the board, if you turn it in and out, it's a little bit easier to see. So they drew it that way, and I think it's sort of a little bit better. Okay, so what they've shown is a molecule like this, in this fashion. Right, and let's just forget about everything else, we'll just take the alkene into it, right? As we have this reaction take place, right, we can sort of see the molecule like this, right? How these are both on the same face, right? And when we bend it outwards, right, what's going to happen is both the protons are going to be effectively coming up, and both the R groups are going to be going back, okay? So again, take a look through your book, try to convince yourself of that. But again, even if it's difficult seeing it, just recognize that in this case, when you're doing them on the ring, there could be confusion, right? On a diene, on the alkene, if they're on the same face, they're going to be on the same face in the product. In this case, where you might get confused, and where I could see you getting confused, is sort of, if they're both on the outside, right, then they're both going to be on the same face. If they're both on the inside, then whatever's on the inside of this is going to end up on one side of the molecule. Whatever's on the outside is going to end up on the other side of the molecule. And if you can draw it and convince yourself of that, that would be great, but I recognize that may be a bit of a challenge. But try to convince yourself. The book has nice diagrams of it. But again, the outside are going to be on the same one side of the molecule, the inside will be on the other side, once you draw into the S-cis kind of configuration. So again, if I went ahead and I did this with the other molecule, so in this case the product would be, so I think this confused it a little bit, but in this case the product would be right? And then likewise, if you just use the same logic, maybe it's easier to see this with just the alkene, but if you use the same logic for the other one, again, now the R, one R is on the inside, the other R is on the outside, and so when the bond actually forms, right, now what you're going to end up with is one side and the other side, okay? So again, there's the stereochemistry that's involved that has to do with this sort of this sort of thinking about it through the S-cis configuration. Again, if you think about it like a sort of fashion, yeah. So, well, this doesn't matter. This is well, it's going to depend. Okay, so the question was asked, how do we tell if it's on one face or the other? In a standard molecule like I've shown here, those would simply result in two enantiomers. The chemistry itself will not dictate which enantiomers are going to form. Okay? 10 minutes. When you begin to bring in substitution here, and say, for example, put an ester there, right? This gets a little bit more complicated because this is truly where visualizing that orbital alignment really came into being, and I think that's probably represents, we can talk about it afterwards, I can sort of show you, but what you sort of have to do is you have to look at all the different possibilities, likely within the endo conformation, because now you're installing another stereocenter. And now they don't become enantiomers, but now they become diastereomers. And in that case, there would be substrate-driven control, which would involve having to actually look at the transition states for the different compounds. And it may be the case that you get a mixture. But you're not going to get selectivity of enantiomers without some other chiral source. But in the case of diastereomers, yes. But I think that's probably a little advanced. Yeah?
So just the basic one you did before, now the return to this mixture?
Yeah, so I would say the things that I want you guys to know, right? So let's just say this. For stereochemistry around, and we'll just simplify this and we won't combine them. Okay? So 3 things with Diels-Alder stereochemistry I want you guys to get used to. Okay? And then we'll move on, and you guys can ask me questions some other time, but I do, we probably got 10 minutes left. So for Diels-Alder selectivity, so I want you guys to know, to be able to draw the endo product, okay? So again, we discussed endo a little bit before, but it's effectively this idea of where your diene is, that's oftentimes where the substitution is. It's sort of kinetic controlled product, okay? I want you to know stereochemistry with cis alkenes, or sorry, with cis or trans alkenes, so i.e. Cis trans or trans dienes. But where it now becomes complicated is if I have to mix these two up. So what I would say is, I think that sort of comes up where the bigger question would come up. So let's just say, just focus on this one or this one. Don't worry about compounds right now that have cis-alkenes or trans-alkenes. If I have a question on a problem set that happens to have those both, just do your best to think about the multiple answers that might arise. And then the final thing that you have to worry about is regioselectivity. Okay, and that's something your book doesn't discuss. So, but you can, there's sort of regioselectivity. Your book doesn't discuss this, but I talk about it in the lecture from last time. Just pay attention for regioselectivity of the electronics of the system. So if you have an acrylate reacting with some type of diene where there's different possible regioselective outcomes, just look at the electronics and try to predict whether it would go one way or another. So those would be the focus, I think, with the Diels-Alder reaction. Okay, so I spent a lot of time on Diels-Alder. There's only 6 minutes left. So what I'm going to do is I'm going to introduce Claisen and Cope chemistry, and then we will continue on it next week. Okay, so the next set of reactions that we're going to learn are basically 3,3 sigmatropic rearrangements. And there's only a couple chapters worth of this, and I'll go back through this because I don't want to rush through it, but I'm just going to sort of introduce you to it right now, just tell you about some of the things that I want you to focus on when thinking about it, so if you want to study it over the weekend. Okay? So 3,3 sigmatropic rearrangements basically involve diene-type systems, right, such as the one that I've shown you here. And what happens in a 3,3 sigmatropic rearrangement is that it's sigmatropic in that you're forming, And that what's happening here is that you're doing, again, it's that same 6 electrons moving simultaneously, very similar to a Diels-Alder reaction, right? And what happens is you effectively make compounds, where's the resonance arrow? You're effectively making new compounds where sort of where the dienes were over here. Sorry, I shouldn't. The color coordinating is not working that much. But basically, you're breaking a sigma bond on this side. Okay? Right? So you're breaking that side. You're forming a sigma bond over on this side. Okay? So you're basically losing a sigma bond on one side, you're forming a sigma bond on the other, and there is this symmetry in here where you're effectively getting very similar molecules. Now this is a reversible process, right? So you can push the arrows in one way, we can also push the arrows in the other way to go back the other way. And so these processes are very often thermodynamically driven. So the product that's going to form in a Cope rearrangement is generally going to be, because the process is inherently reversible, it's going to go with the product that's going to be the lowest in energy. Okay? So just to sort of show an example of where this is the case, this is a reaction called a Cope reaction. And we'll talk about examples where Cope reactions can be thermodynamically stable, or can be thermodynamically driven. But one, again, this can be a little bit confusing, it's the Claisen. We've already learned about one Claisen, right, which you've also known in me getting caught up when somebody was saying something about a Claisen, and I was like, we didn't learn Claisen yet. We learned Claisen condensation. This is the Claisen reaction, or the Claisen rearrangement. And the Claisen rearrangement sort of nicely illustrates how a reaction can be thermodynamically driven. This sort of 3,3 sigmatropic rearrangement can be thermodynamically driven. So the only difference between a Claisen and a Cope, okay, is that there's an oxygen in that ring. And the result of this is going to be that when you do that exact same transformation, the product that you have has a carbonyl, right? And what do we know about carbonyls? Wow, they can be reactive, but they're also stable, right? We've seen instances, for example, enol-keto tautomers. They often want to be a keto rather than the enol form, right? We've seen hemiacetals, right? They don't want to exist as these hemiacetals or hydrates. They'd rather exist as the carbonyls. So carbonyl stability as a thermodynamic sink is a product that you see quite a bit, okay? So these are the two reactions we're going to discuss next week. The one thing that we're going to focus on, and what we'll just focus on the beginning of next week, is that there is also going to be stereochemistry within here. And now in the book, hold on guys, because I'm going to save you time if you just listen a second. There's a discussion on MO theory, okay? The important thing, I'm going to save you guys time. The important point to take home of the MO theory part of that, I'm not going to go into the MO theory as much in depth as the Diels-Alder chemistry. I don't think it really helps us explain that much. But what it does show us is that there is it goes through a chair transition state. And so if you're focusing on the Claisen or the Cope over the weekend, what I'd like you guys to think about and try to rationalize is the stereochemical outcome of these and how it goes through a chair transition state. That's the important part. So that's what I would focus on. We'll discuss that on Monday. And with that, see you guys. No, because the carbonyl, that's what I was saying. And we'll show examples where the Claisen, right? So you can predict examples in the Cope, right? So say, for example, if I had a methyl group there, right? Now I've got a methyl group there. Which way do you think the equilibrium is going to lie? Oh, okay. Right, why? Yeah, so more substituted alkenes are more stable, right? So there's things like that. There's going to be inherent things within there that you'll have to look at and say, this is something that's more stable. And it will be